Hello, I'm Professor Rathod. Now I'm going to present on one of the important topic, namely Carnot and Rankine vapor power cycles. A Rankine cycle is one of an important cycle. In the diagram of this first PPT, you can able to see there is a different equipment or different parts, mainly a boiler, turbine, condenser, and pump. This which works in the cyclic manner. Now, what is actually the cycle, or what is called as vapor power cycle? Any thermodynamic cycle or cyclic process consists of series of thermodynamic operations, also called as processes, which takes place in a certain order, and the initial condition are restored at the end of the processes. When the operations or the processes of cycle are plotted on PV and TS diagram, they form a closed figure, each operation being represented by its own curve. Now actually, what is vapor cycle? Vapor cycle also, all the theory remains same except the working substance, which is steam. Basically, when the water is supplied to the boiler, after heating the boiler produces the steam. So on the strength of steam, that turbine runs, means that thermal energy is going to convert it into the mechanical energy. It means in any vapor cycle, that heat provided to the water, that going to convert it into mechanical work. That is the basic function of this vapor power cycle. Now actually, what is vapor cycles again are used in steam power plants. In a power cycle, heat energy released by the amount of burning of fuel is converted into work, that is nothing but shaft work, in which a working fluid repeatedly performs a succession of processes. In vapor power cycle, the working fluid is water which undergone a change of phase, and that is converted into mechanical work. Now we can see Carnot vapor cycle. Carnot vapor cycle, when steam as a working substance, the important one is a French engineer Carnot has proposed an ideal cycle to calculate the efficiency of heat engine without considering any mechanical details of engine. If we consider 1 kg of saturated water at pressure P1 and absolute temperature T1 as represented by point 1, the cycle is completed in 4 processes or 4 operations. Now if you see the schematic diagram of Carnot vapor cycle, so there are the main equipment like boiler, turbine, condenser, and pump. When in the boiler, when the heat is externally applied to the boiler generates the steam, because boiler is also called as steam generator. Then in the form of steam which goes and falls on the blades of turbine, it means turbine rotates. It means mechanical work is done by the turbine, as the generator is always coupled with the turbine, so there is generation of electricity. Then the remaining steam from the turbine, which goes with the low pressure to the condenser. After supplying the water to the condenser, that steam is condensate. It means steam is going to convert it into the water. Then the water again through the pump, it goes supplies to the boiler. If you see the TS diagram, T is temperature and S is entropy. There are 4 processes. Process 1 to 2. In between 1 to 2, there is a boiler. Boiler generates heat at constant pressure. Then in between 2 to 3 there is a turbine. The eccentric expansion is happening. It means S, that is entropy, remains constant. Then in between 3 to 4 there is condenser. At the constant pressure the entropy decreases, and at the constant pressure that phase is going to change is taking place. It means steam is going to convert it into the water. Then that water supplies to the boiler through the feed pump. So by that time again in between 4 to 1 again the temperature is increases and entropy remains constant, like how the sequence of operation or the sequence of processes ends at 1 and it is starts to the point 1. So now the next, if we see the PV diagram of Carnot vapor cycle, as we have seen the TS diagram. So 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So as we have seen, in between 1 to 2 there was a boiler. That boiler supplies the heat to the system at constant pressure. It means there is increases in entropy but the temperature remains constant. In between 2 to 3 on the PV diagram, that is P is pressure and V is volume. So the turbine in that the temperature decreases as well as somewhat the pressure also decreases. As the temperature decreases, it means pressure also decreases because there is the expansion is happening, and the volume somewhat increases. And in between 3 to 4 there is a condenser. The phase change is happening. It means at the constant pressure there is a decrease in volume, and then again from 4 to 1 there is a pump. A pump tries to supply the water to the boiler. By that time the pressure is increases and somewhat the volumes also reduces. And we have seen what is the TS diagram. T is temperature, S is entropy. On the saturation curve it works. So the mean of saturation curve that is in dome shape, the toppermost point is critical point. The left portion is a liquid saturated region, and the right portion is saturated vapor region, or also called as a superheated region. And in between the dome there is wet region, that means liquid as well as vapor region is there. So that is the importance of PV and TS diagrams. Now the important is, our interest is how to find out the thermal efficiency. As we know, thermal efficiency is net work divided by heat supplied. Net work, that is always work done by the turbine minus work supplied by the pump. It means Q of boiler minus Q of condenser, we can able to see, we can write it. So as I told you, thermal efficiency, or also called as vapor efficiency of Carnot cycle, that is we can say again WT minus WP divided by heat supplied. So finally it is given by 1 minus T1 that is TL in terms of TL, and in terms of TH, TL is lower temperature and TH is higher temperature. So 1 minus TL upon TH is nothing but TH minus TL divided by TH. So efficiency in terms of enthalpy, thermal efficiency can be expressed as thermal efficiency H2 minus H3. So in between 2 and 3, so higher enthalpy minus lower enthalpy, plus in between 4 to 1 there is pump. So H4 minus H1 divided by heat supplied, that is H2 minus H1. So that is how the thermal efficiency as per the terms of temperature and as per the terms of enthalpy, both the way the efficiency can be calculated. Now what is the point to remember about the Carnot cycle? Carnot cycle is purely an imaginary cycle, but all real cycles, all the gas power cycles or the remaining vapor power cycles are constructed based on Carnot cycle. Carnot cycle is one of the theoretical or called as ideal cycle, which is having a higher efficiency, that is always having 100% efficiency, because there is two isothermal process and there is two isentropic processes. It means the process become too lengthy. That is why in actual practice it may not be possible for the actual construction. So but this is the theoretical cycle. But with this basic cycle, remaining every vapor cycles or the gas power is always compared. Now no other engine can have same efficiency as that of Carnot engine working between the same temperature range. These are the points to remember. Now we represent all the processes. If boiler is in between 1 to 2, then the heat of the boiler, heat supplied by the boiler is nothing but H2 minus H1. Now if the turbine is in between 2 to 3, so always the work done by the turbine, that is given by H3 minus H2. If the condenser is in between 3 to 4, then always the heat is rejected, or heat given by the condenser is H4 minus H3. And one of the next process is, if the feed pump is in between 4 to 1, then always feed pump gives us the work is given by H1 minus H4. It means the higher enthalpy minus lower enthalpy always we have to deduct. Then there is the performance criteria for the thermodynamic vapor cycles. So you can read it from the PPT, but what it is important is how to calculate the efficiency ratio. While calculating the numerical efficiency ratio is given by thermal efficiency divided by Rankine efficiency. There is one note you can able to see, the thermal efficiency that can be measured, that can be calculated, 360 multiplied by P divided by M into H2 minus HF1, that is HF is enthalpy of the fluid, we can say. Then one more term is how to calculate work ratio. Work ratio, it is given, that is net work output divided by gross output. Net work output is always work done by the turbine minus work done by the compressor. It means WT minus WP divided by WT. So that is how the work ratio is calculated. And one more important performance criteria is how to find out a specific steam consumption. So that is given by 1 kWh divided by small w, that is 3600 divided by small w. It means 3600 divided by the w, that is in between 0.2 to 3. There is the working element, that is turbine. So H2 minus H3, that is measured in terms of kg per kilowatt hour, where small capital W is what, and small w is net work done or power output, that is given by into bracket H2 minus H3, complete the bracket, kilojoules per kg. That is the performance of criteria of vapor cycle. Now I have taken one of the numerical, how to solve the numerical on the Carnot cycle. I read the numerical for you. If it is asked in the exam, a power plant is supplied with dry saturated steam at a pressure of 16 bar and exhaust at 0.2 bar using steam tables. Find the efficiency of Carnot cycle. Now as I told you, steam table, there is a table that is pressure based, temperature based, enthalpy based, entropy based. There is a table. So if I represent this given data on the TS diagram of Carnot cycle, so the pressure P1 is 16 bar and pressure P2 is 0.2 bar. So from steam table of the pressure based table, 16 bar, for the 16 bar the temperature is that it is given from the steam table, that is 201.4, that is in degrees Celsius, but we have to convert it into the Kelvin, so plus 273, that gives you the absolute unit of temperature, that is in K. Like how corresponding pressure for zero point 0.2 bar, that is P2 is 0.2, for that from the steam table you can able to get that T3 is equal to 60.1 plus 273, that can be 333 K. Now simply we have to calculate the efficiency, so therefore the formula is efficiency is equal to higher temperature minus lower temperature divided by lower temperature. By putting the values, there is, you can able to calculate the efficiency is 29.8%. now one of the second numerical I'll read for you. In a Carnot cycle, heat is supplied at 350 degrees Celsius and it is rejected at 25 degrees Celsius. The working fluid is water, which while receiving heat evaporates from liquid at 350 degrees Celsius to steam at 350 degrees Celsius. From steam tables, the entropy change for this process is 1.438 kilojoules per kg. If the cycle operates in a stationary mass of 1 kg of water, find the heat supplied, work done and heat rejected per cycle. What is the pressure of water during heat reception? Now if I represent it on TS diagram, so T1, that is 350 plus 273, that is 623. T3, that is 25, it is given, plus 273, it means 298 K. Now what it is given is S2 minus S1 is equal to 1.438. What it is given, the entropy change for this process is given, that is 1.438. Now simply what you have to calculate is heat supplied, the first one. The formula is S2 minus S1 multiply by T1 by putting the value heat supplied per cycle, that is 895.87 kilojoules per kg. Second thing, we have to calculate work done per cycle. As we know the formula, work done by this turbine, we can say by the system, that is S2 minus S1 into another bracket T1 minus T3. By putting the values, simply we can able to get the answer is 467.35 kilojoules per kg. Third thing, what we have to calculate is heat rejected per cycle. The formula is S2 minus S1 into T3, so that happens in the condenser. By putting the values, we can able to get 428.52 kilojoules per kg. Now one more thing they have been asked, that is pressure of water during heat rejection. Pressure, it means pressure at condenser, that is from steam table, corresponding to as per the given condition of 350 degrees Celsius. Now from the temperature based steam table, now we get the pressure, that is 165.34 bar. So for the better understanding, I have selected all these numericals for you. Then we will move towards one of we have selected one of the important cycle, vapor cycle, that is Rankine cycle. Now this is on the PPT, it shows the ideal Rankine cycle, in which contain the boiler, the turbine, the pump and the condenser with hot well. If we represent the PV and TS diagram for the better understanding, I have taken in the PV diagram there are two isothermal processes. One is isothermal expansion, another one is isothermal compression. So in between 2 to 3 there is isentropic expansion is happening, and 4 to 1 this process is constant volume process. It means there is increase in pressure. And TS diagram, if we draw the TS diagram on the saturated curve, then 1, 2, 3 and 4, that is in this cycle always T1 equal to T2 and T3 equal to 4. Now this is the ideal Rankine cycle, but our interest is in this how the Rankine vapor cycle is. Now many of the impracticalities associated with the Carnot cycle can be eliminated by superheating the steam in boiler and considering if completely in the condenser. Now the cycle that results in the Rankine cycle, which the ideal cycle of vapor power plants, the ideal Rankine cycle do not involve any internal irreversibilities. Now we can able to see the parts, that is boiler, the turbine, the condenser and the pump, how it can be represented on TS diagram. In between 1 to 2 there are 4 processes. The cycle is completed in the 4 processes. Cycle 1, in between 1 to 2 there is, we have taken pump. So from 1 to 2 there the operation or the process happening is isentropic compression in pump. What happens by that time 1 to 2, when the pump pumps the water to the boiler, there is increase in pressure as well as increase in little increase in pressure and little increase in temperature. So 1 to 2, it means a little bit the entropy remains constant but there is increase in temperature. Then from 2 to 3, what it happens importantly, when the heat is supplied externally to the boiler at the constant pressure, by that time the boiler generates the steam. It is represented from 2 to 3. From 2 to 3 the heat is supplied at the constant pressure. So first from the liquid region to the wet region at constant pressure, then it goes next to the saturated temperature. It means that curves go up to the superheated condition. It means if we form that steam in the superheated condition, it means good quality of steam is obtained, so that maximum efficiency can be given by the maximum work can be given by the turbine if the quality of steam that can be in the form of gas or an idle gas. So that turbine gives you a better quality, better performance of the work. It means there is a better generation of electricity. Then in between 2 to 3 to 4 there is the equipment is a turbine. By that time the expansion is happening. It means releasing in pressure. It means decrease in temperature. That is why it is called as isentropic process, or also called as adiabatic process. It means entropy becomes constant. Then in between 4 to 1 there is one of the element is condenser. By that time the heat is rejected by the condenser. As and when the cooled water is supplied to the condenser, that steam is going to convert it into the water, like how 1 to 2, 2 to 3, 3 to 4 and 4 to 1 the cycle or the operation happens. So like how the Vapour Rankine cycle works. So now our interest is how to calculate the efficiency of Rankine Vapour cycle. So if you can see the schematic diagram of Rankine Vapour cycle, so there is again the boiler, the turbine, the condenser and the pump. If we represent it on TS diagram, so in between 1 to 2 there is turbine, as I told you, from 1 to 2, 2 to 3, 3 to 4 and 4 to 1. 1 to 2 isentropic operation is happened. 2 to 3, so in between 2 to 3 there is condenser and then there is a boiler. So from 4 to 1 what it is happening, the heat is supplied at the constant pressure. So heat is supplied and in the condenser heat is rejected. In 1 to 2 the work done by the turbine, and 3 to 4 the work applied by the pump. So therefore efficiency is Wt minus Wp divided by Q, Wt minus Wp divided by Q, that is heat supplied. So in terms of enthalpy, that is Wt, that is turbine is in between 1 to 2. So therefore H1 minus H2 minus H4 minus H3 divided by H1 minus H4. So if the pump is neglected, then the efficiency will be, efficiency is equal to H1 minus H2 divided by H1 minus H4 if the pump is neglected. So very important. Now the reheat Rankine cycle, all the elements are there, but there is stages of turbine is made, that is high pressure turbine and low pressure turbine. What happens exactly? Reheat cycle, in the reheat cycle, what happens exactly? The aim of reheat cycle is to obtain high efficiency by using high pressure and high steam, at the same time to eliminate the problem of high moisture content at the turbine exit, so that the efficiency can be increased by making the stages. What happens? The vapor is to reheat vapor after it exits from the first stage turbine and redirect to this to reheated vapor into the second stage. Now let us see the stages of the turbine, that high pressure turbine and low pressure turbine. Many of the time in between the high pressure turbine and low pressure turbine, that is connected in between the boiler, so that the reheating is happening. So and now how to find out exactly the efficiency in this diagram, that high pressure turbine and low pressure turbine it shows. If we name it from the top, that is 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So exactly the efficiency of the reheat cycle is again given by net work divided by heat addition or the heat supplied, that is nothing but work done by the turbine minus work by the pump. So in terms of H, if we can able to write, that is H1 minus H2 plus H3 minus H4 divided by heat supplied, that we can able to write as per given condition. The PV and TS diagram was important. There are some of the advantages of the reheat cycle. What is exactly reheat? When we make the stages of the turbine in terms of the high pressure turbine and low pressure turbine. So what is the advantages of it? It improves the thermal efficiency, it increases the network output of the turbine, it reduces the steam rate per kilowatt hour, though there are some of the disadvantages that you can able to read it from the PPT. Now what happens in the vapor power cycle? The working fluid exists in the vapor phase during one part of the cycle in the liquid phase and during the another part, whereas in the gas power cycle the working fluid remains in the gaseous phase throughout the cycle. Then the efficiency, as I told you, the efficiency of reheat cycle, so again these are the advantages. So I have taken some of the numerical on the Rankine cycle. So one of the numerical I have taken it in the Rankine cycle. The dry saturated steam enters turbine at a pressure of 30 bar and exhaust pressure is 0.25 bar. What we have to determine: heat supplied in the boiler, heat rejected in the condenser, turbine work done, thermal efficiency of the Rankine cycle, work ratio, the specific steam consumption, power generation by power plant, if the mass flow rate of the steam is 10 kg per second. So Rankine cycle, how to solve the numerical? Basically we have to solve this numerical on the using by the steam table. If I represent the given data, what it is given, only the two pressures, that is pressure P1 is 30 bar and pressure P2 is 0.25 bar. We have to represent the TS diagram as per the given condition of the numerical. The dry saturated steam enters at the turbine at 30 bar. So it means 1 to 2 there is turbine, 2 to 3 there is a condenser, 3 to 4 there is pump, and 4 to 1 their equipment is boiler. At state 1 the condition of the steam is dry saturated steam. So at the pressure there is 30 bar. So from the steam table of the pressure based table, we have to find out H1 is nothing but Hg, that's a dry steam is nothing but gas, therefore Hg the value is given. Now we have to find out S1, that is specific entropy is nothing but Sg, that is the value of Sg. We have to take it from the table only. Now we'll think for state 2, it means that point 2 the condition or the quality of steam is wet steam there. So we have to write the equation H2 is equal to HF2 plus XHFG2. So at point 2 the pressure is 0.25 bar. From the steam table, corresponding values of 0.25 bar, that is HF we have, HFG we have, from the steam table we get able to get it. So therefore by putting the values of HF2 plus HFG, we can able to calculate the value of X, that is the dryness fraction. So for that, first we have to write the formula again. Entropy S2 is equal to SF2 plus X2 into SFG2. So from the steam table we can able to get the value of SF and SFG. So by putting the values of SF2 and SFG, so S1 is nothing but S2, because as the process is isentropic, therefore entropy remains constant. It means the value of S1 is nothing but value of S2. So we have the value of S1 that is nothing but Sg is nothing but S2. Therefore by putting the corresponding values, we can able to find out the dryness fraction at point 2. That is we have the formula we can able to write, that is 6.184 minus 0.893 divided by the value, that is 6 0.939. From the formula of S2 we can able to find the value of X2, that is 0.76. Therefore we can now able to find out H2 by putting the value of dryness fraction X. We can able to get H2, that is value we have. Now at state 3 the condition of the steam is saturated liquid, because the latent heat has happened, that steam is now converted into the water. Now the pump work we have to find out at this stage. The formula is WP, that is work done by the pump, is equal to specific volume at point 3 into the whole bracket P1 minus P2, the volume, that is 0.001. So whatever the value we have been given, that is divided by 1000. It means that the liters are going to converted into 0.001. Value of P1 that is 30 bar, and that 30 bar must be multiplied by 100, and 0.25 also multiplied by 100. Therefore the value becomes 3000 minus 25. Therefore the answer is 2.975 kilojoules per kg, that is the pump work. So from the steam table we have value of H3 is nothing but HF3, and value of specific volume HF is nothing but Hg. So HVF is nothing but Vg, that is 0.001 meter cube per kg. From that value we have taken for value of small v3, Now for step 4, the condition of the steam is subcooled or compressed liquid. So here therefore we have to write the formula in between the process or the operation 3 to 4, the pump work, that is nothing but H4 minus H3. so if we have to find out H4, then the formula will become WP plus H3 is equal to 2.975 plus 272. Therefore value of H4 is 274.97. now what has been asked after the calculation of step 1 2 3 4 at the condition of 1 2 3 and 4, everything the formula we have been written. Now we have to calculate the values. First one is heat supplied in boiler, that is QS, that is H1 minus H4. Putting the values, already we have calculated H1 and H4, we can able to get the value of 2527 kilojoules per kg. Now second thing what we have calculated is heat rejected in condenser, that is condenser is in between 2 to 3, therefore H2 minus H3 we can able to get after putting the values, that is 1789. Now we have to find out third thing is turbine work done by the turbine, that is in between 1 and 2 there is turbine in this case, therefore H1 minus H2. Putting the values we can able to get the work done is 741 that is 741 kilojoules per kg. Now the fourth thing we have to find out the theoretical efficiency of Rankine cycle. The important one is, that is we know the formula W net divided by QS multiplied by 100. W net is always WT minus WP divided by QS. After putting the value of WT and WP and QS, we can able to get the value is 29.2 percentage, because the efficiency is always measured in terms of percentage. Now next thing we have to find out work ratio, that is WN divided by WT, that is net work already we have, and WT after putting the value we can able to get the ratio is 0.99. Now one more important solution we have to find out, that steam specific consumption, also called as SSC. For that there is formula 3600 divided by W net, 36 divided by we have the value of W net, so we can able to get the value of 4.87 in the terms of kg per kilowatt hour. And one of the last answer we have to find out is power generation by power plant. The formula we have, that is W is equal to M into W net. So M, that is the mass, it is given in the numerical, and we have the W net, therefore power generated by power plant, the answer is 7380.25 kilojoules per second. We have given M mass is 10 kg per second. So dear friend, for you I have I will solve here one more next numerical for you, which is the university based numerical. Steam power plant operates on the Rankine cycle. Steam is delivered to the turbine at 38 bar and the temperature of 350 degrees Celsius. The steam from a turbine expands up to a condenser pressure of 0.08 bar. So from the given things what you have to find out, the first thing is drainage fraction of steam entering condenser, the heat rejected in condenser, and Rankine efficiency. So from the given thing we have to represent this on the Rankine cycle on the TS diagram as per the given condition of the steam delivered to the turbine at about 38 bar. It means the steam reaches at the superheated condition. So if I represent in between 1 to 2 there is turbine, 2 to 3 there is condenser, in between 3 to 4 there is pump, and importantly in between 4 to 1 there is boiler. We know the heat is supplied at the constant pressure, it means from liquid state to there is change in phase, it means latent phase is happening. So by crossing the wet region, the steam above the saturated temperature which goes to the superheated condition, if we compare the quality of superheat with T soup and T sat. It means superheated temperature and saturated temperature. So at the given condition of the pressure at 38 bar, the value of T sat saturated temperature, that is 247.3, and we have the superheated temperature if that is 350 degrees Celsius. So if you compare T soup and T sat, it means the value of T soup is greater than T sat. It means the quality of steam is superheated. So they always called what is the quality of steam. Therefore the answer is the quality of steam is superheated. Now at condition 1, if we have to find out the value of H1, S1, etc., etc. So at condition 1, the pressure is 38 bar and the temperature is 350 degrees Celsius. From that we have to find out value of H1 and value of S1. So S1 is specific entropy, H1 is specific enthalpy. So for the process or the operation 1 to 2, that is isentropic process, it means entropy remains constant. Therefore we write S1 is equal to S2. Now come to at point 2, the pressure is 0.8 bar. Now we have to write the equation S2 is equal to SF2 plus X2 SFG2. We have to write the value of S2 SF2 from the steam table. We can able to find the value of dryness fraction at point 2. The answer is 0.79. Now we have to write the equation of H2, that is HF2 plus X2 HFG2. HFG, that is the latent heat, that is the enthalpy of a fluid to gas. So by putting all the values we can able to get the H2. Now the H3 is nothing but HF3. So from the steam table we can able to get it, that is 173.9 kilojoules per kg at point 3. So therefore we can write the formula, that is of WP is nothing but H4 minus H3 is equal to, the standard formula is 0.1 into the whole bracket P1 minus P2. By putting the values of H3, P1 and P2, we can able to calculate H4. So by putting the values we can able to get H4, that is 177.692. that is always measured in kilojoules per kg because these are the enthalpies. One more answer we have to find out of heat rejected in condenser. As we know, the condenser is in between 2 and 3. Therefore H2 minus H1, if I write those values, I can able to get the heat rejected answer is 1898.52 kilojoules per kg. And one more important answer is how to find out Rankine efficiency. For this, what formula we have to write in terms of H is 1 minus into the whole bracket H2 minus H3 divided by H1 minus H4. See the formula neatly and clearly. So 1 minus I can able to putting the values of H1, H2, H3 and H4. I can able to get the efficiency, value of efficiency is 0.35026. It means the efficiency is 35.2%. Now dear friend, this is all about the vapor power cycles. As I told you, what is vapor power cycle? When the steam is going to converted into the mechanical works, when the water is taken into the boiler and heat is supplied, that going to form the steam, and that steam is going to converted into mechanical work. That is whole about the vapor power cycles. Thank you. Thanks a lot.